Elon Musk calls Mars humanity's backup plan. But here's the disturbing reality: even after a full-scale nuclear war, Earth would still be far more survivable than Mars on its very best day. The air would still be breathable, water would still exist, gravity would still protect your body. On Mars, none of those things are guaranteed. If you're watching this right now, pause for a moment, because what you're about to hear may completely change the way you think about humanity's dream of becoming a multi-planet species. Prepare yourself. Let's begin. Step outside on a morning in Arizona. The air hits your skin before your brain registers it cool, faintly dry, already carrying the promise of heat to come. You breathe in, your lungs expand without effort. No decision made, no instruction given. The atmosphere just presses gently against your chest, and your body does what it has always done, what it was built to do, what it will do approximately 23,000 times today without a single conscious thought from you. 70 years of that, every single day, and not once will you think about it. Now take it away completely. The atmosphere on Mars is not thin in the way people say. The air is thin at high altitude. This is something categorically different. The atmospheric pressure on the Martian surface sits at roughly 0.6% of what you experience standing anywhere on Earth. The summit of Mount Everest, the place that kills trained mountaineers, that demands supplemental oxygen, that pushes the human body to its absolute outer edge, has a pressure roughly 3 times higher than what Mars offers at ground level. 3 times. The most hostile terrain on Earth's surface is still dramatically more survivable than an ordinary Tuesday afternoon on Mars. The composition makes the pressure problem worse, not better. 95.3% of the Martian atmosphere is carbon dioxide, according to the NASA Mars fact sheet. Breathable oxygen accounts for less than 0.2% of what surrounds you out there. So when people say you would need oxygen tanks on Mars, they are already thinking about the wrong problem. Oxygen delivery is not what fails first. What fails is the mechanical act of breathing itself. Your lungs need ambient pressure, real, physical pressure, pushing inward to execute gas exchange at the cellular level. Without it, the process collapses entirely. You would not suffocate from lack of oxygen. You would suffocate from the absence of pressure to make oxygen useful at all. That distinction is not a technicality. It is the difference between an engineering problem and a biological impossibility. There is a threshold in aerospace medicine called the Armstrong limit, named after American physician Harry Armstrong, who identified it in the 1930s. When ambient pressure drops below 6.3% of standard sea level pressure, roughly equivalent to an altitude of 19 kilometers, something happens that has nothing to do with oxygen availability. Water boils at 37 degrees Celsius. Body temperature. No heat source required. The fluid in your body, which stays liquid under normal conditions because atmospheric pressure keeps it suppressed, reaches its boiling point simply because the containment pressure is gone. Mars sits at 0.6%, so far below the Armstrong limit that the limit itself becomes almost a footnote by comparison. What this means in physical terms is not abstract. The moisture lining your eyes begins to vaporize. The saliva in your mouth does the same. The fluid cushioning your joints, the water threaded through your tissues, all of it begins transitioning toward gas because the pressure holding it liquid no longer exists. Blood does not boil dramatically in the cinematic sense because proteins and dissolved solids raise its boiling point slightly. But the gases dissolved in your bloodstream: nitrogen, oxygen, carbon dioxide begin escaping out of solution as bubbles. The same mechanism that causes decompression sickness in deep sea divers, except instantaneous and total, and without any possibility of a slow ascent to fix it. Take a bottle of carbonated soda, shake it hard. Now unscrew the cap. Everything inside was held in equilibrium by pressure. The gas dissolved into the liquid, stable, contained. The moment the pressure releases, the liquid erupts. Bubbles surge upward. Foam spills over the edge. The dissolved gas violently reclaims its gaseous form because nothing is holding it back anymore. Your body is that bottle. The Martian atmosphere is the act of unscrewing the cap. At least you will not need to worry about finding a bathroom, because every fluid in your body will be leaving on its own schedule first. The full sequence of what happens to an unprotected human on the Martian surface plays out across roughly 30 to 60 seconds before unconsciousness, followed rapidly by death. The precise order depends on variables like decompression speed, but the destination does not change. There is no path through this that ends in survival. The Martian sky, what little of it qualifies as sky at all, is not merely hostile. It is structurally, chemically, and mechanically incompatible with what 300,000 years of human evolution produced on a planet that was extraordinarily generous about the conditions it provided. Every system in your body, every reflex, every automatic process, every piece of cellular machinery was calibrated for one full atmosphere of pressure and 21% oxygen concentration. Strip those two conditions away, and the machinery does not struggle to adapt. It simply stops. The way a combustion engine stops when you remove the air intake. Not gradually, not with warning, just stops. And what makes this particular danger so strange, so quietly unsettling, is that the Martian sky looks almost peaceful in photographs. That pale butterscotch haze, the low sun casting long shadows across rust-colored plains. There is something almost cinematic about it, something that reads, at a distance, as austere and beautiful rather than immediately lethal. Nothing about its appearance signals what it actually is. An environment that would kill an unprotected human being faster than almost any other surface in the solar system. The sky you breathe in without thinking every morning in Arizona. It is the product of an atmosphere 167 times denser than what Mars provides. It is the product of billions of years of geological and biological processes conspiring to produce exactly the conditions animal life requires. It is, by any objective measure, an extraordinary gift that evolution has trained you to receive without gratitude, without awareness, without a single moment of recognition. On Mars, that gift does not exist. And no amount of engineering enthusiasm changes the starting point. The atmosphere is not merely inadequate, it is, for human biology as it currently exists, functionally the same as no atmosphere at all. But if somehow you survived the first 5 seconds outside your suit, the temperature would finish the rest in a way you never could have anticipated. -62 degrees Celsius. That is the average surface temperature on Mars, per NASA's recorded data. Read that number once and file it away as very cold, and you have already missed the most important part of what that number means, because the average is almost the least frightening thing about Martian temperature. The swing is what breaks you. Within a single Martian day, surface temperature can shift by as much as 170 degrees Fahrenheit, roughly 94 degrees Celsius, from one end of the day to the other. At the equator, a Martian morning can open at -100 degrees Celsius. By early afternoon, that same location might climb to +20 degrees Celsius. Not warm, exactly, but above freezing. Then the sun descends, and the temperature falls off a cliff again. -60, -80, back toward -100 before the next cycle begins. No place on Earth produces temperature swings remotely close to this within a single day. The most extreme continental deserts, the harshest polar regions, none of them approach this range. On Earth, the atmosphere acts as a thermal buffer. It absorbs heat during the day and releases it slowly through the night, smoothing the curve, keeping the extremes from becoming catastrophic. The system is imperfect, but it works. It has worked for billions of years. On Mars, that buffer is almost entirely absent. This is the thermal paradox at the heart of Martian climate. And it is worth understanding precisely because it is so counterintuitive. The atmosphere on Mars is so thin that it cannot retain heat. The sun rises, and it does rise on Mars, a smaller, paler disk than we see from Earth, but present, and it begins delivering solar radiation to the surface. The surface absorbs it. Temperatures tick upward, but the moment that heat tries to radiate back into an atmosphere that might hold it the way Earth's atmosphere holds it, there is almost nothing there to do the holding. The energy escapes directly into space. The sun is technically warming the ground, but the warmth cannot accumulate in any meaningful way because the medium required to trap and store it barely exists. The closest analogy on Earth standing under a heat lamp in a room with no walls. The lamp is real. The heat coming off it is real. You can feel it on the side of your body facing the lamp. But the moment you step slightly away, or the moment the lamp angles away, every bit of that warmth vanishes into open air. No residual heat, no retained warmth in the surrounding environment, just immediate cold filling back in from every direction the moment the direct source moves. That is what every Martian day looks like, scaled to planetary proportions. Now build a colony inside that environment and think through what it demands. Every human habitat on Mars must maintain a survivable internal temperature continuously, not seasonally, not during particularly cold stretches, but every hour of every day without interruption, from the moment the first settler arrives until the moment the last one leaves or dies. There is no mild season. There is no temperate period where systems can rest, where maintenance can be deferred, where energy consumption can ease. The cold is always there, just outside the wall, pressing inward, waiting for any gap in the thermal envelope. A heating system failure on Mars is not an inconvenience. It is not the equivalent of a broken furnace in Minnesota where you call a repair service and wear an extra sweater for a day. A heating failure on Mars is a countdown. The internal temperature of a habitat begins dropping immediately, and given the thermal conditions outside, it drops fast. Within hours, pipes freeze. Within hours, water systems fail. Within hours, equipment designed to operate within specific temperature ranges begins malfunctioning. Within hours after that, the humans inside are fighting hypothermia in the only place they were supposed to be safe. The comparison that fits a tent in an Alaskan winter, in the middle of a blizzard, with no firewood and no rescue coming. Except the tent is pressurized, sealed against a toxic atmosphere. And the nearest person who could help is somewhere between 55 million and 400 million kilometers away, depending on where Earth and Mars happen to be in their respective orbits at that moment. The energy numbers make this concrete in a way that is difficult to absorb. Calculations from MIT's research into Mars colonization scenarios estimate that heating alone for a colony of 1,000 people could require energy expenditure exceeding the total annual energy budget of a small American city. That is not the total energy budget of the colony water processing, food production, oxygen generation, equipment operation, lighting, computing, transportation. That is heating. One line item, one of dozens of systems that must run continuously and simultaneously just to keep people alive. For context, a small American city is not an energy light operation. It runs hospitals, schools, traffic systems, commercial refrigeration, industrial equipment, residential heating and cooling across thousands of homes. The energy infrastructure behind it is vast and expensive and took generations to build. On Mars, that entire energy output or its equivalent would be consumed just by the task of keeping 1,000 people from freezing to death. And this is not a problem that engineering optimism can wish away. The cold is not a variable that can be negotiated with. It is not a challenge that improves as technology advances. The physics of heat retention on Mars are set by the atmospheric density. And the atmospheric density is not going to change on any timescale relevant to human colonization plans. What you build has to work against those conditions from day one, at full capacity, forever. What emerges from all of this is something that has no real precedent in the entire history of human civilization. Every society ever built on Earth existed within an environment that, at minimum, tolerated human presence. The harshest places humans have historically settled: Arctic tundra, high-altitude deserts, equatorial rainforests still offered some version of an atmosphere that could be breathed, temperatures that the human body could survive with adequate shelter, and a thermal environment that at least occasionally cooperated. The engineering challenge was always one of adaptation, of working with a difficult environment rather than against one that was fundamentally and permanently opposed to your survival. Mars does not adapt. Mars does not cooperate. Mars presents a thermal environment so hostile and so constant that every single calorie of heat required to keep a human being alive must be generated artificially, continuously, without pause, without backup from the planet itself, and without the possibility of rescue if something goes wrong. That is not an engineering problem. That is a civilizational trap unlike anything our species has encountered in 300,000 years of finding ways to survive in difficult places. But temperature and pressure, brutal as they are, remain things we can build walls against. There is another threat on Mars that no wall, no roof, no thickness of construction material can stop. And it comes from beyond the galaxy itself. Nobody thinks about Earth's magnetic field at breakfast. You pour your coffee, check your phone, maybe glance out the window at whatever the morning looks like, and the entire time, completely without your awareness, an invisible planetary defense system is operating at full capacity around you. Right now, as you watch this, billions of high-energy particles are streaming toward Earth from the sun and from deep space solar wind, cosmic rays. Charged particles accelerated to fractions of the speed of light by events happening millions of light years away. And right now, Earth's magnetic field is deflecting nearly all of them, bending their trajectories, sending them looping around the planet and away. It has been doing this every second of every day for 4.5 billion years, without interruption, without maintenance, without anyone noticing. That shield is the reason life exists on this planet. Not oxygen, not liquid water, not the right temperature range. All of those things matter. But they matter because the magnetic field made them possible in the first place by protecting the atmosphere and the surface long enough for biology to take hold. Remove the shield, and the atmosphere erodes. Remove the atmosphere, and the water escapes. Remove the water, and the temperature extremes become unsurvivable. The magnetic field is not one item on a list of things that make Earth habitable. It is the precondition for most of the others. Mars had one once. That is the detail that changes everything. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, which entered Martian orbit in 2014, spent years studying what happened to Mars's atmosphere and why. The conclusion was stark. Mars lost its global magnetic field approximately 4 billion years ago, likely when its molten iron core cooled and solidified, shutting down the dynamo process that generates a planetary magnetic field. Once the field collapsed, the solar wind went to work directly on the Martian atmosphere, stripping it away particle by particle over hundreds of millions of years. The thick atmosphere Mars once possessed, the one that may have supported liquid water on its surface, was gradually eroded into the ghost of an atmosphere that exists today. No magnetic field, almost no atmosphere, 2 layers of protection gone simultaneously, and neither one is coming back on any timescale that matters to anyone alive today or for thousands of generations to come. What this means for a human being standing on the Martian surface is not theoretical. Data collected by the Radiation Assessment Detector instrument aboard NASA's Curiosity rover measured surface radiation on Mars directly, over an extended period, under real Martian conditions. The result radiation levels on the Martian surface run approximately 100 times higher than what is considered safe for human exposure on Earth. Not 100% higher, 100 times higher. The baseline, the floor, the minimum exposure a settler would receive simply by existing on Mars on an unremarkable day with no solar event occurring is already at a level that has no parallel in normal human experience anywhere on Earth, outside of certain very specific medical and industrial environments. The numbers make this tangible. A standard chest X-ray delivers approximately 0.1 millisieverts of radiation, a unit used to measure biological radiation dose. NASA sets a career exposure limit for its astronauts at 500 millisieverts, recognizing that exceeding that threshold meaningfully elevates cancer risk. A Mars settler, according to Curiosity's measurements, would absorb approximately 300 millisieverts per year from background radiation alone on calm days, with no solar storms, just the ordinary continuous bombardment that comes with living on an unshielded planet. That is 60% of NASA's entire career astronaut limit, consumed every single year, just from ambient conditions. To be clear about what 300 millisieverts per year actually means in live terms, it is the equivalent of receiving roughly 3,000 chest X-rays annually, every year, without choosing to, without a medical reason, simply as the cost of existing in that environment. The biological consequences accumulate across multiple systems simultaneously. The NASA Human Research Program, which exists specifically to study what space environments do to human physiology, documents a 5 to 10% increase in cancer mortality risk for individuals exposed to Mars-level radiation over extended periods. That number sounds modest until you multiply it across an entire colony and hold it next to every other risk those same people are already carrying. Beyond cancer, radiation at these levels causes cataracts. The lens of the eye accumulates damage that is slow, progressive, and permanent. It causes DNA strand breaks in cells throughout the body, which the body's repair mechanisms handle up to a point, but not indefinitely and not without error. Some of those errors accumulate in reproductive cells, which means the damage does not stop with the individual exposed. It potentially carries forward. None of this begins after 20 years of exposure. None of it waits for some threshold to be crossed before the biological toll starts. The accumulation begins on day one. The first morning, a settler wakes up on Mars and walks to whatever passes for a window in a Martian habitat. The radiation dose for that day is already being absorbed. There is no grace period, no acclimatization phase during which the body adjusts and the risk stays low. The counter starts immediately and runs continuously for as long as that person remains on the surface. You will not need to worry about SPF 50 sunscreen on Mars. There is no SPF rating that exists on any scale relevant to this situation. The engineering responses to this problem are real but brutally constrained. Habitat walls can be thickened. Regolith Martian soil can be piled onto structures to add mass shielding. Underground habitats offer significantly better protection than surface structures. Since rock and soil absorb radiation effectively, these approaches help. They reduce the dose. They bring numbers down from catastrophic toward merely very bad. But they cannot bring the dose to zero. They cannot replicate what Earth's magnetic field and atmosphere provide, essentially for free, to every living thing on this planet. The shielding required to match Earth's protection level would require mass and construction scale that is currently beyond any realistic colonization scenario. And even the best shielding does nothing for the moments settlers spend outside their habitats during maintenance operations, during exploration, during any of the practical activities that a functioning colony would require. The invisible shield that Earth carries, the one you have never once thought about while going about your day, is the product of a planet-sized iron core still generating electromagnetic energy after 4.5 billion years. It is not something that can be packed into a rocket and shipped to Mars. It is not something that can be engineered around with sufficiently clever architecture. It is simply absent. And its absence is written into the Martian surface in every particle of radiation's curiosity recorded, day after day, in data that does not soften or equivocate. And this is only the radiation on the quiet days. Because there are days when the sun decides to send something far worse toward Mars, and when that happens, everything we have just described becomes almost beside the point compared to what comes next. The sun is not a stable object. It never has been. What we experience from Earth's surface is a filtered, softened, magnetically redirected version of what the sun actually produces. And even that version, after passing through 4.5 billion years of planetary shielding, is enough to cause sunburn in 20 minutes of unprotected exposure. What the sun produces without filters, without distance, without a magnetic field standing between it and a surface, is something in a different category entirely. Solar particle events are the sun's episodic eruptions, moments when the solar surface releases enormous quantities of high-energy charged particles, primarily protons, accelerated to velocities that can carry them across interplanetary space within minutes to hours. They are not predictable in the way weather forecasts are predictable. They are not slow-building phenomena that give days of warning. A significant solar particle event can go from detection to arrival at a planetary surface in less than 30 minutes. The particles themselves travel at a meaningful fraction of the speed of light. On Earth, a solar particle event registers as a disruption to radio communications, a particularly vivid aurora, maybe some minor technical issues with satellites in high orbits. The magnetic field absorbs the punch. The atmosphere catches what gets through. The surface, where human beings live, experiences essentially nothing. Life continues. Nobody notices. On Mars, an identical event reaches the surface almost unimpeded. The radiation dose delivered by a major solar particle event to an unprotected or inadequately shielded surface on Mars can climb into the thousands of millisieverts within a matter of hours. To calibrate what that means, acute radiation syndrome, what used to be called radiation sickness, begins at doses around 1,000 millisieverts received over a short period. The symptoms are not subtle. Nausea and vomiting begin within hours. Over the following days, severe fatigue, hair loss as follicle cells fail, immune system collapse as bone marrow stops producing white blood cells at normal rates, hemorrhaging as platelet production drops. At doses above 4,000 to 5,000 millisieverts received acutely without significant medical intervention, mortality rates climb steeply. At doses above 6,000 millisieverts, survival without advanced medical care becomes unlikely. A large solar particle event can deliver doses in that range to an unprotected surface in hours. Research published by scientists at the University of New Hampshire in 2021 analyzed historical solar particle events and modeled their effects on Mars surface conditions. Their findings indicated that a major event could expose a Martian surface to radiation equivalent to approximately 150 full-body CT scans delivered not over a medical procedure lasting minutes, but compressed into a window of a few hours. 150 full-body CT scans in an afternoon. Now add the communication problem, because this is where the situation moves from dangerous to structurally inescapable. The signal delay between Earth and Mars ranges from 4 minutes at closest orbital approach to 24 minutes when the planets are on opposite sides of the Sun. This is not a technical limitation that better equipment can solve. It is a consequence of the speed of light and the distances involved, and it is absolute. When NASA's monitoring systems on Earth detect a significant solar particle event in progress, which itself requires detection, analysis, confirmation, and decision-making before any warning is issued, that warning then travels toward Mars at the speed of light. 4 to 24 minutes later, it arrives. The particles themselves, moving at a significant fraction of the speed of light, may arrive at Mars at roughly the same time as the warning, or in some cases before it, depending on the geometry of the event and the delay in detection and transmission. The warning system that works on Earth, where light-speed communication is effectively instantaneous for any practical purpose, where emergency broadcasts reach their destinations in milliseconds, fundamentally does not work across interplanetary distances. Settlers on Mars may receive a warning telling them a solar particle event is occurring at roughly the same moment the event's radiation front is already washing over their habitat. The engineering solution exists, and it is what it is. Go underground, deep underground, or under several meters of compacted Martian regolith piled onto habitat roofs. Rock and soil are effective radiation shields. Mass stops particles effectively, and Mars has abundant mass in the form of its surface material. A shelter with sufficient overhead coverage can reduce solar particle event exposure to survivable levels. But think through what this solution actually means for the humans living inside it. During the Cold War, the United States built fallout shelters, underground bunkers stocked with supplies, designed to shelter civilian populations from nuclear fallout in the event of nuclear exchange. The psychological literature on those shelters and on the populations that actually had to use similar structures during wartime is consistent. Even 2 weeks of underground confinement produces measurable psychological deterioration, anxiety, tension, interpersonal conflict, sleep disruption, a pervasive sense of helplessness that does not fully resolve even after emergence. Those shelters were designed for 2 weeks, for a temporary emergency, with the knowledge that the world outside, when the occupants finally emerged, would still be the same world they had left. On Mars, the shelter is not temporary. The underground bunker is not an emergency measure activated during a crisis and then vacated when the crisis passes. It is the default condition. It is where settlers live because the surface, even on ordinary days, delivers radiation doses that accumulate toward dangerous levels, and because when solar particle events occur, and they occur multiple times per year during periods of high solar activity, the surface becomes acutely lethal within hours. The bunker is not a refuge from the planet. The bunker is the only way to exist on the planet at all. The settlers who choose Mars, and they would be choosing it voluntarily, presumably with full knowledge of these conditions, would not be explorers in the romantic sense of the word. They would be people who spend the majority of their lives underground, in sealed corridors and pressurized rooms, venturing to the surface only when conditions permit, always monitoring solar weather data, always calculating the radiation budget remaining in their exposure allowance for the year, always aware that the sky above them is not a backdrop to their lives, but an active threat to their survival. Not because of war, not because of crime, not because any human institution placed them there, because the universe simply arranged the physics of this particular planet in a way that makes the surface hostile to the biology that evolved on a different, far more protected world. The imprisonment is not punitive, it is cosmic, and it is permanent for as long as anyone lives there. There is something in that which resists easy framing. The human mind can process danger, can adapt to hardship, can find meaning in struggle. But there is a specific quality to confinement without end, to threat without reprieve, to a sky that is not merely indifferent, but actively lethal, that has no real precedent in the catalog of difficult environments humans have historically managed to inhabit and even flourish within. Every hard place on Earth eventually offers something: a season that eases, a landscape that opens, a sky that, however cold or stormy, can be stood beneath without dying. Mars offers none of that. The sky on Mars is the threat, and the only answer to it is to not be under it. You can go underground to escape the radiation. You can build thick walls to hold the heat. But there is something on Mars that no structure can keep out because it seeps through every gap, clings to every surface, and it is waiting for you right now in every grain of red soil. Pick up a handful of soil in Iowa. Really hold it for a moment. It is dark, almost black in good farmland, dense with organic matter, threaded with the remnants of decomposed plants, alive with microbial activity that has been building and rebuilding that soil for thousands of years. It smells like something. That smell is biological activity, fungal networks, the quiet chemical work of a living system. Farmers know that smell. They trust it. For 10,000 years of human agriculture, soil has been the foundation of civilization, not metaphorically, but literally. Every city ever built, every population ever fed, every empire ever raised rested ultimately on the productivity of ground that could grow things. Soil is life. That is not poetry. That is the operating premise of everything humanity has ever built. On Mars, the soil is poison. NASA's Phoenix lander touched down near the Martian North Pole in 2008 with instruments specifically designed to analyze the chemical composition of Martian regolith, the layer of loose, fragmented material covering the surface. What Phoenix found was not expected in its concentration. The soil contained perchlorate, written chemically as ClO4-. At concentrations ranging from 0.5 to 1% by weight, NASA's Curiosity rover, operating thousands of kilometers away in a completely different geological region, confirmed the finding. Perchlorate is not a localized anomaly in one region of Mars. It appears to be a global feature of the Martian surface. 0.5 to 1% perchlorate. The number needs context to land properly. The maximum contaminant level for perchlorate in drinking water set by the United States Environmental Protection Agency is 0.00007%, 7 parts per billion. The concentration found in Martian soil exceeds that safe threshold by a factor of roughly 10,000 to 20,000 times. This is not trace contamination. This is not background noise at the edge of detection limits. This is perchlorate so thoroughly embedded in the Martian surface that it constitutes nearly 1% of the soil by mass. Everywhere the soil has been tested. The biological consequences of perchlorate exposure are well documented. At lower doses, it interferes with the thyroid gland's ability to absorb iodine, disrupting the production of thyroid hormones that regulate metabolism, cardiovascular function, and neurological development. Chronic low-level exposure causes hypothyroidism fatigue, cognitive impairment, weight gain, cardiovascular complications. At higher concentrations, perchlorate is a strong oxidizer, meaning it releases oxygen rapidly in chemical reactions and can ignite or accelerate combustion when it contacts organic material under sufficient heat. The same property that makes perchlorate useful as a rocket propellant component makes concentrated Martian soil a chemical hazard in the presence of heat sources. A colony that must maintain internal temperatures above freezing at all times is a colony that is perpetually managing heat sources in close proximity to a surface compound that behaves like an oxidizing agent. Mars apparently decided that a lethal atmosphere and deadly radiation were insufficient, so it added explosive soil chemistry to complete the package. But the perchlorate in the bulk soil, as serious as it is, is not the primary delivery mechanism for human exposure. The dust is. Martian dust particles are smaller than 3 microns in diameter, finer than the PM 2.5 particulate matter that defines severe air pollution alerts in Earth's most contaminated cities. They are not just small. They carry a strong electrostatic charge, a consequence of the ultraviolet radiation environment and the chemical properties of the Martian surface. That charge makes them clingy in a way that defies casual engineering solutions. Martian dust does not simply settle on surfaces and stay put. It adheres. It works itself into joints and seams. It coats visors and optical surfaces. It finds pathways through multi-layer filtration systems that were designed with terrestrial dust behavior in mind. NASA's Mars rovers have struggled with dust accumulation on solar panels since the first missions, and rovers are not inhabited, do not require airlocks, do not have the constant in and out traffic of humans moving between pressurized habitats and the exterior surface. A human colony would be different. Suits come back inside after surface operations. Equipment moves between environments. Airlocks cannot achieve perfect decontamination on every cycle. The dust gets in. Not hypothetically it gets in, because everything about its physical properties is optimized, accidentally, but effectively, for penetrating barriers. And when it gets in, it brings its perchlorate content with it. Dust particles smaller than 3 microns, once inhaled, do not stay in the upper respiratory tract where the body's natural clearance mechanisms can handle them. They penetrate into the deep lung tissue, into the alveoli where gas exchange happens, and they accumulate. The perchlorate they carry makes direct contact with lung tissue. Over months and years, the cumulative effect is not survivable through simple medical management. The comparison that fits living inside a chemical processing facility where the ventilation system cannot be turned off and cannot be left. Not visiting it, not working a shift and going home, living in it every hour with no alternative location available and no transport coming to take you somewhere cleaner. The exposure is not an occupational hazard with a dose limit and a rotation schedule. It is a permanent condition of existence on that planet. Every surface operation adds to the contamination load inside the habitat. Every airlock cycle is a negotiation between the need to function as a colony and the imperative to keep the interior as clean as possible. The filtration systems required to manage Martian dust, its size, its charge, its chemical reactivity, would need to operate continuously, at high efficiency, without failure, for the entire duration of the colony's existence. A filter failure is not a maintenance inconvenience. It is the beginning of a slow accumulating medical crisis that affects every person breathing the habitat air, the soil beneath a settler's boots, the dust coating the outside of their suit, the fine particles that work their way through every barrier designed to stop them. None of it is inert. None of it is merely dirty. All of it is chemically active in ways specifically hostile to human biology, distributed globally across a planet-sized surface and present in concentrations that have no safe analog in any environment humans have previously inhabited. And if daily perchlorate dust is not terrifying enough on its own, wait until the entire planet decides to gather all of that dust together and hurl it directly at your colony for months at a time. Mars has seasons. It has weather patterns. It has atmospheric dynamics that follow recognizable physical principles, pressure gradients, temperature differentials, fluid dynamics playing out in a thin layer of carbon dioxide that barely qualifies as an atmosphere. In that sense, Mars is a planet with meteorology. The problem is what that meteorology produces at its most extreme and how often it produces it. Planet-encircling dust storms are not a theoretical risk on Mars. They are a documented, recurring feature of the Martian climate cycle events in which suspended dust particles spread across the entire planetary surface. blotting out direct sunlight across a region the size of every continent on Earth simultaneously, and sustaining those conditions for weeks to months. The 2018 global dust storm is the most recent major example in the record. It began in late May of that year, grew rapidly, and within weeks had encircled the planet entirely. It persisted for approximately 3 months before gradually clearing. NASA's Opportunity rover, a machine that had operated successfully on the Martian surface for 14 years, far beyond its original 90-day design, life lost power when the storm blocked the sunlight its solar panels needed to function. The rover went into a low-power emergency mode and waited. The storm cleared. The sunlight returned. Opportunity never woke up. Its batteries, depleted beyond recovery during the months of darkness, could not recharge sufficiently to restore operations. A machine that had survived 14 Martian years of everything the planet could throw at it was ended not by a mechanical failure, not by a software fault, but by a dust storm that simply took away its energy source for long enough. Opportunity was a rover. It did not need heat. It did not need air. It did not need water. It needed only power. And the storm denied it, that for long enough to be fatal. A human colony needs all of those things simultaneously, continuously, without interruption. The domino sequence that a global dust storm initiates in a human settlement is not complicated to trace, but its endpoint is not survivable without extraordinary preparation. Dust accumulates on solar panel surfaces and reduces their output. As the storm intensifies and dust density in the atmosphere increases, incoming solar radiation drops toward negligible levels. Solar panels that were already operating at reduced efficiency compared to Earth, because Mars receives only 43% of the solar energy per square meter that Earth's surface receives, purely due to its greater distance from the Sun, now drop to near zero output. During a major global storm, solar energy availability on the Martian surface falls by approximately 99% compared to clear sky conditions. 43% of Earth's solar input, reduced by 99% during a storm, means the colony is operating on roughly 0.4% of what Earth receives on a clear day. Solar power, under those conditions, is not a reduced resource. It is a failed resource. Power loss cascades immediately. Heating systems draw on electrical power, lose heat, and the interior temperature begins dropping toward the ambient Martian exterior within hours. Air filtration and circulation systems require power. Water processing and pumping requires power. The lighting that makes the habitat psychologically survivable, the communications equipment, the medical systems, the food production infrastructure, all of it draws from the same power supply. When that supply collapses, these systems do not fail gracefully. One by one, in a manageable sequence, they fail together, or in rapid succession, each failure accelerating the next. The domino chain from dust to darkness to cold to failed air processing to failed water systems plays out across days, not weeks. The colony's reserves of power, water, and heat, whatever they managed to store in anticipation of the storm, determine whether anyone is still alive when the dust finally clears. No earthly natural disaster creates this particular cascade. A hurricane cuts power, but the air remains breathable, and the temperature, while potentially dangerous, does not drop toward negative 100 degrees Celsius within hours. A blizzard isolates a community, but sunlight returns within days, and rescue can reach the affected area. A volcanic eruption, a flood, an earthquake. All of these are events with endings, with outsides, with the possibility of external response. A Martian global dust storm has no outside. It covers the entire planet. There is no unaffected region to evacuate toward. There is no rescue flight coming from Earth on any timeline that matters. The minimum transit time between planets is 6 to 9 months. and a rescue mission cannot be launched on the day the storm begins and arrive in time to matter. The settlers waited out, with whatever they stored, in the dark and the cold and the degrading air quality, for however long the storm decides to last. And the critical detail, the one that reframes everything about how a Mars colony must be conceived and operated. Global dust storms on Mars are not rare events. They do not represent the outer edge of a probability distribution that a colony might reasonably hope to avoid. They occur on a cyclical basis. Mars scientists do not model them as low-probability catastrophes. They model them as scheduled events with uncertain timing. The question a Mars colony must answer is not whether a global dust storm will occur during the colony's operational lifetime. The answer to that question is yes. The question is only when and whether the colony's energy reserves, its backup systems, and its nuclear power infrastructure are sufficient to survive it when it arrives. A colony without a nuclear reactor running in parallel with its solar array is a colony that a global dust storm can kill. The math does not negotiate. 43% solar input reduced by 99% is not a power budget any human settlement can survive on. The settlers who look up at a Martian sky beginning to take on that particular ochre haze that precedes a major storm are not watching a natural spectacle. They are watching their energy supply begin to disappear and calculating in real time whether what they have stored is enough to last until it comes back. Us. We have talked about the air, the radiation, the dust, and the storms, but surviving all of that requires the three most fundamental things any human being needs: water, food, and energy. And on Mars, all three must be fought for every single day in ways no survival engineer in the history of our species has ever had to confront. Turn on a faucet. Water comes out. Cold, clean, immediate, arriving at your hand within a second of the decision to want it. You do not think about where it came from. You do not think about the reservoir, the treatment plant, the distribution network, the pressure system maintaining flow through hundreds of kilometers of pipe. You certainly do not think about what it cost to build and maintain all of that, because the cost is so distributed across so many people and so many decades of infrastructure investment that it has become effectively invisible. You just turn the handle, water appears, you use it and forget about it. On Mars, every single liter of water is the output of an industrial process. There is no rain on Mars, no rivers, no lakes, no ocean anywhere on the surface, and no prospect of one forming on any timescale relevant to human planning. Water exists, that much is established. It is locked in the regolith as ice, mixed into the frozen soil at varying concentrations depending on latitude, and it accumulates in larger quantities at the two polar caps, where it forms visible deposits of water ice and dry ice layered together. The water is there. The problem is everything required to turn it from frozen mineral content into something a human being can drink. Extracting water from Martian regolith means heating frozen soil to temperatures sufficient to sublimate or melt the water content, then capturing the released vapor before it escapes into an atmosphere so dry it would reabsorb moisture almost instantly, then condensing that vapor back into liquid form, then running it through filtration systems capable of removing perchlorate contamination at concentrations thousands of times above safe thresholds. Each step in that chain requires energy, significant, continuous energy, and equipment that must operate without failure in an environment that degrades equipment faster than any conditions on Earth. A single extraction system breakdown does not mean the colony drinks less water. It means the colony has no pathway to new water at all until repairs are completed. The closed-loop recycling system fills part of the gap. Every molecule of water that enters the colony must be recovered and returned to circulation. Sweat from physical exertion passes through moisture recovery systems in suits and habitat air processing units. Exhaled breath, which carries significant water vapor with every exhalation, runs through condensation recovery. Urine, all of it, from every person, every day goes into water reclamation processing. This is not a theoretical future technology. The International Space Station has operated a water recovery system on these principles since 2008, recovering approximately 93 to 95% of water from urine and humidity on a continuous basis. The ISS system works. The principle is sound, but the ISS receives resupply missions approximately every 3 months, carrying replacement filters, spare parts, maintenance components, and emergency water reserves. A cargo vehicle can reach the station from Earth's surface in roughly 6 hours. If a critical component fails on the ISS, the timeline for a replacement to arrive is measured in weeks at most. On Mars, the nearest resupply is 6 to 9 months away by the fastest available transit, and that assumes a vehicle is already prepared and waiting for launch at the moment the failure occurs. The water recycling system on a Mars colony cannot fail? Not because failure is unacceptable in an abstract sense, but because failure means the colony begins dying of thirst within days. And nothing in the universe can stop that outcome on the timeline that matters. The entire settlement is drinking from the output of a single closed-loop system with no external backup and no possibility of emergency resupply. The comparison that captures this living in Las Vegas, a city built in the middle of a desert, dependent on the Colorado River for its water supply, except the Colorado River has been permanently cut off. Every alternative water source has been severed, and the only thing standing between the city and mass dehydration is a single water recycling machine running on a 9-volt battery with no replacement batteries available anywhere within 6 months of travel. Then there is food. Growing food on Mars is not simply a matter of bringing seeds and soil and applying enough light and water. Every variable that agriculture on Earth takes as a given must be artificially manufactured and maintained simultaneously, at continuous cost, against a planetary environment that provides none of them naturally. Mars receives 43% of the solar energy per square meter that Earth's surface receives, because it sits roughly 1.5 times farther from the sun. That reduced light is not merely inconvenient for plant growth, it is below the threshold required for many crop species to photosynthesize efficiently without supplemental artificial lighting. Artificial lighting requires electricity. Electricity is the resource the colony is already spending on heating. Water processing, air management, and life support across every other system. Food production competes directly with survival functions for power that is already severely constrained. The greenhouse structures required to grow food present their own engineering problem at a scale that is easy to underestimate. Plants need atmospheric pressure to grow, not necessarily Earth-level pressure, but enough to prevent their internal fluids from behaving the same way human fluids do below the Armstrong limit. The greenhouse must maintain internal pressure substantially above the near vacuum outside. That means building a pressure vessel, a structure capable of holding significant differential pressure across its entire surface area without any leak developing over years of operation, while simultaneously withstanding the thermal stress of temperature swings approaching 94 degrees Celsius per day. The abrasive and chemically reactive Martian dust accumulating on its exterior, ultraviolet radiation degrading its transparent panels, and the occasional solar particle event adding radiation loading to the structural materials. A Mars greenhouse is not a greenhouse in any sense the word normally carries. It is a pressure vessel, a radiation shield, a thermal management system, and an agricultural facility simultaneously, built to operate without maintenance access for extended periods in conditions that would challenge Earth's most demanding industrial infrastructure. Each salad grown inside that structure represents the output of all of that engineering, all of that energy, all of that maintenance and monitoring and continuous system management. The production cost per kilogram of food grown on Mars, accounting for the infrastructure required to make growing possible at all, would be astronomical by any earthly comparison. A Tesla, roughly speaking. Per serving of vegetables and DoorDash does not deliver to coordinates 140 million kilometers from the nearest restaurant. Water and food together represent the biological minimum, the floor beneath which human survival is not possible regardless of how well every other system is functioning. And both of them, on Mars, exist only as the output of complex, energy-hungry, failure-intolerant industrial systems that must operate continuously and perfectly, simultaneously, with no external support for the entire duration of anyone's presence on the planet. Water and food are already challenges that border on the insurmountable, but all of those systems need one thing to function. And that thing on Mars is being withheld by the planet itself in ways you have not yet considered. Every system described in the previous 7 parts of this story runs on electricity, the heating that keeps settlers from freezing, the water extraction and recycling that keeps them from dying of thirst, the air processing that keeps the oxygen concentration breathable, and the carbon dioxide from accumulating to toxic levels. The food production infrastructure, the medical equipment, the communication systems, the lighting, the computers managing every automated process simultaneously. Pull the power, and all of it stops. Not gradually, not partially all of it, in sequence, within hours to days, depending only on how much residual heat and stored water and bottled oxygen the colony managed to accumulate before the failure. The energy problem on Mars is not a problem of scale. It is a problem of source, and Mars has methodically eliminated every energy source that humans have historically relied on. One by one. Solar power is the obvious first candidate. It is clean. It requires no fuel supply chain, and the technology is mature and well understood. The problem is the math. Mars receives 43% of the solar energy per square meter that Earth's surface receives. A solar array that would power a specific number of homes in Arizona needs to be more than twice as large on Mars to deliver the same output before accounting for dust accumulation on the panels, which begins immediately and reduces efficiency continuously until the panels are cleaned. Cleaning solar panels is a manual operation requiring suited human workers or robotic systems, both of which require time, energy, and maintenance. And as established in the previous section, a global dust storm reduces available solar energy by approximately 99% from already reduced Martian baseline levels. Solar power on Mars is a supplemental resource at best. As a primary power source for a colony that must not experience power interruptions, it fails the most basic requirement: reliability. Wind is the other renewable candidate, and Mars does have wind, sometimes strong wind, capable of moving dust across planetary distances. The problem is the atmosphere carrying that wind. Power generated by a wind turbine is proportional to the density of the air moving through it. Martian atmospheric density is roughly 1% of Earth's. A wind turbine operating in Martian atmospheric conditions, even in high-velocity wind events, generates power output orders of magnitude below what an equivalent turbine produces on Earth. The wind that drives planet-encircling dust storms powerful enough to end the operational life of a NASA rover, would barely spin a turbine to useful output because there is simply not enough mass in the moving air to transfer meaningful kinetic energy to the blades. Wind power on Mars is not a marginal resource. It is essentially not a resource at all in any practical energy planning sense. This leaves nuclear fission as the only power source that can actually meet the colony's needs. NASA and the United States Department of Energy have been developing what they call the kilopower reactor, a small fission surface power system capable of producing 10 kilowatts of electrical output from a compact, transportable unit. 10 kilowatts is modest by any standard, roughly enough to power a few average American homes, but the design is scalable, and multiple units operating in parallel can supply a colony's baseline needs independent of sunlight or atmospheric conditions. The reactor runs on enriched uranium, produces steady output regardless of dust storms or day-night cycles, and represents, by current engineering assessment, the only realistic path to energy independence for a Mars settlement. The complications are not trivial. The reactor must be transported from Earth. It is heavy, it is expensive, and the launch and transit risks associated with flying an enriched uranium fission reactor across interplanetary space are not insignificant in either engineering or political terms. It requires enriched uranium fuel that must also be sourced, processed, and transported from Earth, with no local supply chain available. It requires nuclear engineers capable of operating and maintaining its specialists, whose expertise takes years to develop, and who must be present on the colony, not as occasional visitors, but as permanent residents whose primary function is keeping the reactor running. And it requires redundancy, because a single reactor failure affecting the colony's sole power source triggers the same cascading collapse described above, just from a different initiating event. The dependency chain this creates is total. Energy powers heating. Heating maintains the temperature differential that keeps people alive. Water processing requires energy to heat regolith, run pumps, operate filtration, oxygen generation. The electrolysis of water into hydrogen and oxygen requires energy. Food production requires energy for lighting, heating the greenhouse, running nutrient circulation systems. Medical equipment requires energy. Communications require energy. Every link in the survival chain connects back to the same single source. 1,000 people, with their entire survival apparatus, fed through one reactor. The comparison: an entire city of 1,000 residents, powered by a single diesel generator, no backup unit, no fuel depot, no grid connection, and the nearest fuel station 100 million miles away, depending on orbital positions. When the generator runs, the city lives. When it stops, the countdown begins. What this does to the psychology of a community is not something engineering specifications capture. Every morning, someone in that colony wakes up and checks the reactor status before they check anything else. Not out of professional duty, though it is that too. Out of the knowledge that the answer to that check is the answer to whether today is a day that continues normally or a day that begins a crisis no one on the planet can resolve from the outside. The reactor is not infrastructure in the background sense that a power grid is infrastructure in a modern city, invisible, assumed, noticed only when it fails. On Mars, the reactor is the foreground. It is the first thought and the last thought and the constant background hum of anxiety running beneath everything else the colony does. That is not an inconvenience. It is a psychological condition with no precedent in settled human civilization. Every society ever built on Earth existed within an energy environment that, at minimum, offered alternatives. Fire could be gathered, rivers could be dammed, windmills could supplement. The sun, at least, rose every morning with predictable generosity. The idea that a community's entire survival could depend on a single machine, with no fallback and no rescue, is new. It has no historical analog, and the people living inside that condition would know it every day without relief. And if you think that everything outside the atmosphere, the radiation, the dust, the storms, the water, the food, the power is already frightening enough, we have not yet talked about what is happening inside the bodies of the settlers themselves. Because Mars does not only attack from the outside, it is quietly destroying them from within, every day, every hour, and it cannot be reversed. Every step you take is a negotiation. Not a conscious one you have never once thought about it this way, but a negotiation, nonetheless, between your body and the planet beneath your feet. When you stand up from a chair, your legs push against a floor that pushes back with the full weight of Earth's gravity. And every muscle fiber involved in that movement is maintaining itself precisely because it has to perform that task repeatedly, all day, every day, without exception. When your heart beats, it is beating against the resistance of pumping blood upward through your body, against gravitational pull, a constant low-level cardiovascular workout that never stops, not even while you sleep. When your bones bear your weight as you walk across a room, the mechanical load traveling through your skeleton is the signal your bone-building cells use to determine how much structural material to maintain. The signal says you are needed here. Keep building. Stay dense. Stay strong. Gravity is not just a force acting on your body. It is the invisible trainer that built your body, that maintains it daily, that has been shaping the architecture of every human skeleton and heart and muscle system for 300,000 years of evolutionary history on a planet with one standard gravity. You have never signed up for a gym membership with Earth. You have never chosen to participate in this training program. It simply runs continuously in the background of your existence, keeping you structurally capable of the life you are living. On Mars, the trainer shows up at 38% capacity, and no one knows what that does to a human body over years, because no human being has ever lived at 0.38 G for longer than a few hours. The closest data available comes from the International Space Station, where astronauts live in microgravity effectively 0 G for missions ranging from 6 months to a year. The findings from NASA's Human Research Program are precise, and they are not reassuring. After 6 months in microgravity, astronauts lose between 1 and 2% of their bone mineral density per month, not per year per month. The rate of loss is roughly 10 times faster than the most accelerated osteoporosis seen in elderly patients on Earth. Muscle mass decreases by approximately 20% over a 6-month mission, with the greatest losses in the postural muscles of the lower body, the ones that exist specifically to work against gravitational load. The heart, no longer required to pump blood upward against a full gravity gradient, begins to remodel itself. Its muscle walls thin slightly. Its shape shifts subtly towards spherical. Its output efficiency in the context of a gravitational environment decreases. Astronauts returning from 6 months on the ISS cannot walk unassisted when they first land. They are carried from their capsule. They undergo months of physical rehabilitation to rebuild what 6 months of weightlessness took from them. The bone density loss is partially recoverable, but studies suggest that repeated long-duration missions accelerate the permanent loss component, the portion that does not fully come back, regardless of how much rehabilitation is completed. Now, the critical distinction: Mars is not zero gravity. 0.38 G is not nothing. It exerts real mechanical load on the body. The honest scientific answer about what it does to human physiology over years is that nobody knows, because the data does not exist. No human being has spent months or years at 0.38 G. No simulation on Earth can replicate it continuously. You cannot turn down gravity in a laboratory. The closest analogs are bed rest studies, in which subjects remain horizontal for extended periods to reduce gravitational loading on the musculoskeletal system. And those studies confirm the bone loss mechanism, but cannot perfectly model the Mars scenario. What researchers can say is this: 0.38 G is probably better than 0 G for maintaining bone and muscle mass. The mechanical signal is still present, still telling osteoblasts to keep building. But whether it is sufficient, whether 38% of Earth's gravitational load is enough to prevent the gradual hollowing of bone structure over 5 years, 10 years, a lifetime, is a question that current science cannot answer because the experiment has never been run. the mechanism is not mysterious, even if the Mars-specific outcome is uncertain. Bone is not a static material. It is living tissue, constantly being broken down by cells called osteoclasts and rebuilt by cells called osteoblasts in a continuous remodeling cycle. Under normal gravitational loading, the two processes stay roughly in balance breakdown and rebuilding occurring at comparable rates. Maintaining density, reduce the mechanical stimulus that tells the osteoblasts their work is needed, and the balance shifts. The osteoclasts continue their work. The osteoblasts slow down. The net result is progressive loss of bone mineral density from the inside out, a process invisible until it has progressed far enough to show up on a bone scan, or more dramatically, as a fracture from a load the bone should have been able to handle. Think of a steel bridge that carries no traffic for 20 years. The steel does not immediately rust through, but without the constant load cycling that actually keeps certain structural metals in a state of maintained integrity, without the regular stress that metal responds to, subtle degradation begins. The bridge looks the same from the outside. The engineering analysis tells a different story. On Mars, every settler's skeleton is that bridge, carrying a fraction of the load it was designed for, in an environment that provides no compensatory mechanism and no possibility of briefly returning to full load to reset the process. The cardiovascular system follows a parallel logic. On Earth, the heart's left ventricle must generate enough pressure to push blood upward against gravity to the brain, to the shoulders, against the constant downward pull that would otherwise pool all your blood in your lower body. That demand keeps the heart muscle strong, reduce gravity to 38%, and the heart's workload drops correspondingly. Over time, cardiac muscle that is not being challenged at its normal load begins to adapt downward, the same way any muscle adapts to a reduced demand by reducing its capacity to meet demands it is no longer experiencing. For a settler who never leaves Mars, this adaptation is a one-way process. The heart becomes calibrated to 38% gravity. It becomes efficient at 38% gravity. And if that settler were ever to return to Earth to stand up in 1 standard G, for the first time in years, the cardiovascular system would face a demand it had spent years becoming less capable of meeting: the risk of orthostatic intolerance, of the heart simply not generating enough pressure to maintain cerebral blood flow against full gravity, is real. The risk of cardiac events in a system that has adapted away from the capacity needed to function at 1G is not theoretical. The good news on Mars? You will jump considerably higher than you ever could on Earth. The bad news: your bones may not survive the landing. Counter movement exists. Exercise protocols, resistance training, pharmaceutical interventions, electrical stimulation of muscle and bone. All of these have been tested on ISS crews with varying degrees of success. They slow the losses. They do not prevent them. And they require time, energy, equipment, and medical expertise that a Mars colony must continuously maintain and provide, adding another dependency to the list of things that cannot be allowed to fail. A settler who cannot exercise due to illness or injury begins losing bone density faster. A colony that loses its exercise equipment to a mechanical failure has a medical crisis in slow motion unfolding over months. What the data from the ISS most clearly establishes is that human physiology was not designed for reduced gravity environments. That adaptation to them is real and measurable and partially irreversible, and that the mitigation strategies currently available buy time rather than solve the problem. For a 6-month mission, the losses are manageable with rehabilitation. For a permanent settlement with no return mission for people who will spend years or decades at 38% G, the long-term physiological trajectory is genuinely unknown. And the honest answer from every researcher working in this area is, we do not know what happens, and we cannot know until someone actually does it. That uncertainty is not a reason for optimism. It is a reason for extreme caution about a decision that cannot be undone once made. What happens to the adults who choose to go is troubling enough, and it is at least a choice they make with the information available. But what happened to the adults has been studied, has been measured, has at least the partial comfort of being known. What happens to children born on Mars, those who never make any choice at all? That story is not just more frightening. It raises the deepest ethical question humanity has not yet confronted. There is a thought experiment that clarifies something important about what a Mars colony eventually becomes, if it endures long enough to become anything at all. Imagine the first generation of settlers adults who were born on Earth, grew up under one standard gravity, developed their full skeletal density and cardiac capacity and muscular architecture in an environment that demanded all of it. They arrive on Mars as complete biological products of Earth, carrying in their bodies the full inheritance of a species that evolved under 1G for hundreds of thousands of years. They experience the physiological deterioration described in the previous section, the bone loss, the cardiac remodeling, the muscle atrophy, but they arrive with reserves. Their bones begin dense. Their hearts begin strong. The losses are erosions of a starting point that was built for a different, more demanding world. Now imagine a child born on Mars to those settlers. That child's bones develop under 38% gravity from the first day of life. The skeletal system of a developing human does not arrive fully formed. It builds itself in response to the mechanical environment it experiences during growth. The bones of a child who grows up at 0.38 Ag will be longer, because reduced gravitational compression during longitudinal growth allows bones to extend further. They will be thinner in their cortical walls, because the mechanical signal telling the bone to maintain a certain wall thickness for structural support under load is calibrated to 38% of what that signal would be on Earth. Their mineral density will be lower, because the remodeling cycle that builds density is driven by the loads being applied, and those loads are a fraction of what human bone development evolved to respond to. The cardiovascular system develops by the same logic. A heart that grows from infancy to adulthood at 38% gravity builds itself to meet the demands of 38% gravity. It does not build excess capacity for a gravitational environment it has never experienced and has no biological reason to anticipate. It builds exactly what the environment requires and nothing more. By the time that child reaches adulthood, their body will be a precise biological expression of Mars, adapted to it, calibrated for it, functional within it, and permanently, irreversibly incapable of functioning anywhere else. One standard gravity would not feel like home to that person. It would feel like being slowly crushed. The heart, calibrated for 38%, could not generate the pressure differentials required to maintain cerebral perfusion against full gravitational pull. The bones, developed at lower mineral density and with thinner cortical walls, would face structural loads they were never built to carry. Standing up on Earth, simply standing up, a task every human takes for granted, could trigger cardiovascular collapse. Walking could fracture bones that look normal from the outside, but were built by a body that never needed them to be stronger. There is no rehabilitation pathway for this. There is no exercise protocol that retroactively rebuilds a skeleton that formed under reduced gravity. The architecture was laid down during development, during the years when the body was deciding what kind of body it needed to be. Those decisions cannot be undone by any intervention currently available or plausibly available within any realistic technological horizon. The person born on Mars is not trapped by a decision they made. They are not confined by law, or by circumstance, or by any human institution's choice. They are confined by the physics of their own skeleton and the biology of their own cardiovascular system built, precisely and permanently, for a world they can never leave. No word in English captures exactly this. Imprisonment implies punishment, implies a decision made by someone with power over someone without it. Exile implies a home that was left behind. Captivity implies something that could, in principle, end. What faces a child born on Mars is something without a name in any language, because nothing like it has ever existed before in the history of our species. The place of birth has always been, in every human life, before this. The beginning of a story that could go anywhere. For a child born on Mars, the place of birth is the entire story, beginning and end and everything in between, written by gravity before they take their first breath. The ethical question this raises does not have a clean answer, and anyone who tells you it does is not engaging with it honestly. When the first settlers make the decision to have children on Mars, and if any permanent colony is to exist, that decision will eventually be made. They are making a decision on behalf of a person who does not yet exist, about a constraint that person will never be able to escape, and about a life that person will never have chosen. Every human born on Earth inherits constraints: genetic, economic, geographic, cultural. But no human born on Earth is physically prohibited from going anywhere else on the planet, or anywhere else in the solar system, by the body they were given at birth. The constraints of earthly life are circumstantial. The constraint of being born on Mars is biological, absolute, and permanent. Is there moral authority to make that choice for another person? The philosophical traditions that have thought most carefully about consent, about the ethics of bringing beings into existence, about what obligations are created by the act of creating a life, none of them developed in a context where the planet of birth was a life sentence written in bone density and cardiac muscle. The frameworks do not map cleanly. The answers are not obvious. And the people who will face this decision in practice will be far from Earth, far from ethicists and courts and the accumulated moral wisdom of human civilization, making it in real time under conditions of extreme stress and limited resources. What is clear is this: the first generation of Mars settlers can theoretically change their minds. The mission can be aborted, a return vehicle can be launched. The choice to go to Mars, for adults who make it with full information, carries within it at least the theoretical possibility of reversal. The colony's children carry no such possibility. Their commitment to Mars is total before they are old enough to understand what commitment means. Their citizenship of an unlivable planet is written into their bodies by the physics of a world that asked them nothing and took everything. There is something in that which sits outside the ordinary catalog of things we worry about when we worry about the risks of Mars colonization. The technical problems are enormous, but they are the kind of problems that engineers can at least attempt to solve. The biological trap of a generation born into permanent gravitational exile is not a technical problem. It is a human problem, a moral problem, a problem that asks what kind of species we are and what kind of species we want to become, and whether the answer to how do we survive as a civilization can ethically include by creating people who have no choice but to be part of the answer. No framework developed by 300,000 years of human civilization on Earth prepared us for that question. We invented it ourselves, with rockets and ambition and the very best of intentions. We have talked about what Mars does to the body, but what does it do to the mind, to the human spirit, forced to live under conditions no one in the entire 300,000-year history of our species has ever had to endure? Call 911. That is the entire decision tree for a medical emergency in the United States. 4 words, 1 action, and within 8 minutes, an ambulance arrives carrying paramedics with equipment, training, and a direct line to an emergency physician who can begin directing care before the vehicle reaches the hospital. Within 2 hours, a surgeon with 10 years of specialized training and a team of anesthesiologists, nurses, and technicians operating inside a facility with imaging equipment, a blood bank, a sterile operating theater, and an intensive care unit immediately adjacent, that surgeon has resolved the problem. The patient goes home the next day. The mortality rate for an appendectomy performed under these conditions approaches 0. This is so routine that the word routine barely captures it. Millions of people have had their appendix removed and filed it mentally alongside other minor life inconveniences, a week of soreness, a small scar, a story told occasionally at dinner. The machinery behind that outcome is so vast, so expensive, so deeply embedded in the infrastructure of modern civilization that it has become invisible. The hospital did not appear because you needed it. It was already there, staffed and equipped and waiting. The product of decades of construction and training and supply chain management and regulatory oversight, funded by taxes and insurance systems and institutional investment accumulated over generations. On Mars, none of that exists, and the appendix does not know it is on Mars. The signal delay between Earth and Mars ranges from 4 minutes at closest orbital approach to 24 minutes when the planets are on opposite sides of the Sun. This is not a problem that better communication technology can solve. It is a consequence of the speed of light across interplanetary distances, and it is absolute. When a settler on Mars begins experiencing the classic symptoms of appendicitis, the initial peri-umbilical pain migrating to the lower right quadrant, the fever, the rebound tenderness, and contacts Earth for medical guidance, the first response arrives somewhere between 8 and 48 minutes after the question was sent. A back-and-forth consultation that on Earth would take 30 seconds of real-time conversation requires hours on Mars. By the time a physician on Earth has asked 3 clarifying questions and received the answers, the patient's condition has been evolving for 6 hours without intervention. There are no specialist surgeons on a Mars colony. There cannot be, in any realistic early settlement scenario, a colony of 100 to 1,000 people. The scale that serious Mars colonization proposals discuss for initial phases cannot support the full spectrum of medical specialization that a modern hospital provides. A general surgeon, an emergency physician, perhaps a psychiatrist, perhaps an internist. This is the realistic medical complement for an early colony. Assuming the extraordinary expense of training and transporting medical personnel is considered worthwhile against the other demands on the mission's resources and weight budget. No neurosurgeon, no cardiac surgeon, no trauma team, no anesthesiology department, no blood bank with type-matched reserves, no MRI machine. The magnetic field requirements and weight make it impractical for early missions. No CT scanner for the same reasons. No ICU with continuous monitoring, ventilators, and the nursing staff ratio required to run one effectively. What a Mars colony has is a general practitioner or two, a supply of medications and surgical instruments brought from Earth and not resupplied for 6 to 9 months at minimum, and a telemedicine connection to Earth physicians who can advise but cannot intervene, cannot see the patient directly, and cannot receive real-time updates because the signal delay makes real-time anything physically impossible. The conditions that modern medicine treats as manageable inconveniences become, in this context, genuine threats to life. Appendicitis, caught early and operated on promptly, is trivially survivable. Appendicitis that perforates because the diagnosis was uncertain, the surgeon was unavailable, or the anesthesia ran short becomes peritonitis, becomes sepsis, becomes a condition with a mortality rate measured in tens of %, even in well-equipped hospitals. A heart attack in a settler with no cardiac surgeon, no catheterization lab, no thrombolytic therapy available. The outcome depends on timing, on what medications happen to be on hand, and on how much relevant training the colony's generalist physician has in a specialty they may not have practiced in years. A severe traumatic brain injury from an accident during a surface operation, a category of emergency that requires neurosurgical intervention within hours to prevent permanent damage or death, has no pathway to a good outcome on a planet where the nearest neurosurgeon is 8 months away by spaceship. The comparison that fits is not modern medicine's failures. It is medicine before modern medicine existed. Frontier settlements in the American West in the 1850s operated with a physician present only if one happened to be in the vicinity. Trained to a standard that would be considered dangerously inadequate today, working with instruments and medications that bear almost no resemblance to what a current emergency room stocks, those settlements lost people to infections, to injuries, to childbirth, to conditions that today's medical system resolves before breakfast. The death rate from treatable causes was genuinely elevated compared to settled areas with better access to care. Historical accounts from frontier communities are full of deaths from what we would now consider minor medical events. Mars is worse than that. At least in the American frontier of 1850, a physician from the nearest town, even if that town was 3 weeks away by horse, could eventually arrive. A surgeon summoned from a city 2 months' journey distant was at least theoretically on the way. On Mars, no one is coming. The nearest help is not delayed by primitive transportation. It is delayed by the laws of physics governing the minimum transit time between two planets in elliptical orbits. And those laws do not negotiate or make exceptions for medical emergencies. The International Space Station, for all its isolation at 400 kilometers above Earth's surface, has a medical protocol that acknowledges this limitation honestly in any serious medical emergency. The astronaut is evacuated. The Soyuz capsule can return a crew member to Earth in roughly 3.5 hours. The medical treatment happens on Earth, where the full apparatus of modern medicine exists. The ISS does not attempt to be a hospital. It attempts to stabilize and transport. Mars has no evacuation option. There is no 3.5-hour return flight. There is no option that gets a patient to a hospital within any medically relevant time frame for acute emergencies. The colony must handle what it faces with what it has. And what it has is a fraction of what medicine has determined is necessary to handle the full range of medical emergencies that arise in a population of human beings living full human lives. On Mars, needing a doctor urgently means waiting 9 months for the next Earthbound ship and hoping you are still around when it departs. The medical infrastructure problem is not a secondary concern in Mars colonization planning, to be addressed after the more glamorous engineering challenges of propulsion and habitat design. It is a fundamental constraint on what kind of life the people living on Mars can actually have. Every settler on Mars lives with the knowledge that a specific category of medical events, the ones that require specialist intervention, major surgery, or intensive care, exists outside the boundary of what can be done for them. That knowledge reshapes the relationship between a person and their own body. Every symptom carries a different weight when the treatment options available do not include most of what modern medicine offers. A headache is not just a headache. A chest pain is not something to monitor over the next few days to see how it develops. The margin for error that modern medicine has built into the ordinary experience of illness and injury simply does not exist. The human body breaks down. That is not a flaw. It is the nature of biological systems operating over decades. The entire infrastructure of modern medicine exists because we recognize that reality and built a response to it at enormous collective expense over many generations. Mars colonists carry that same biological reality, the same appendixes, the same coronary arteries, the same bones that fracture and spines that herniate into an environment where the response to breakdown is whatever the colony's 2 physicians can manage with the equipment that fit in the cargo manifest and the medications that have not yet passed their expiration date. The body can endure and adapt. That is what evolution teaches us. But what about the mind? What about the part of a human being that needs connection, needs open space, needs the quiet knowledge that leaving is possible? What happens when all of that is stripped away completely? Not for a few weeks, but for years, for decades. The HISEAS project. Hawaii Space Exploration. Analog and simulation placed small crews of researchers inside a dome on the slopes of Mauna Loa. Hawaii's volcanic landscape, chosen for its Mars-like terrain, for missions lasting 4 to 12 months. The participants could not leave the dome without wearing simulated spacesuits. They communicated with the outside world through a 20-minute simulated signal delay. They cooked from shelf-stable supplies, maintained equipment, conducted research, and lived in close quarters with the same small group of people for the duration of the mission. The psychological findings from HISEAS and from the Parallel Mars 500 simulation conducted in Moscow, in which 6 volunteers spent 520 days in a sealed facility simulating a round trip to Mars, were consistent across both programs and consistent with each other. By the 8-month mark, participants were showing measurable increases in depression and anxiety scores. Sleep quality degraded. Interpersonal conflict, initially manageable, escalated into persistent tensions that the confined environment made impossible to fully resolve. Motivation dropped. The cognitive flatness that researchers call anhedonia, the diminished capacity to experience interest or pleasure, appeared in multiple participants across both studies. These people were on Earth. They could have opened a door at any moment and walked outside. In the case of genuine emergency medical, psychological, any kind the option to leave existed, they knew it existed. Their brains, on some level below conscious awareness, knew it existed. And it was still not enough to prevent significant psychological deterioration over the course of the mission. On Mars, there is no door that leads outside. There is a door that leads to a suit-up room, that leads to an airlock, that leads to a surface that will kill you within a minute if your suit fails. The psychological literature has a term for the situation. Mars creates a no-exit condition. It is not merely being confined. It is being confined with the knowledge that the confinement is structural, that it is not temporary in any meaningful sense, that the outside world does not contain a version of safety that can be reached. The difference between confinement with a theoretical exit and confinement without one is not a matter of degree. It is a different category of psychological experience, and the human brain did not evolve any reliable mechanism for processing it over the long term. The isolation on Mars operates at multiple levels simultaneously. And this is what makes it different from the isolation studied in analog missions. There is spatial isolation, the inability to move outside a defined pressurized envelope without full life support, which restricts the physical world to a set of corridors and rooms that can be walked end to end in minutes. There is social isolations, the same faces, the same voices, the same small group of people constituting the entire human population of your world, forever, with no possibility of meeting someone new, no possibility of escaping a person you have come to find difficult, no privacy in the deep sense of simply being somewhere that the people around you are not. There is informational isolation, every communication with Earth delayed by 4 to 24 minutes each way, making real-time conversation impossible, collapsing all connection to the wider human world into an asynchronous exchange of messages that feel, over time, less like conversation and more like letters to and from a world that has moved on without you. And there is emotional isolation of a specific and particularly painful kind, the inability to be physically present for the lives of the people you love. A parent on Mars cannot attend their child's graduation on Earth. They learn about it in a message 20 minutes after it was sent, and their response arrives 20 minutes after that. A sibling's wedding, a friend's funeral, a parent's final illness. All of these events occur on a planet that a Mars settler cannot reach in a time frame that no available transportation can compress. The people they left behind age. Children grow into adults the settler does not recognize from one transmission to the next. Parents die, friends move, change, build lives that the settler is increasingly absent from. The connection to Earth does not hold steady. It attenuates. The world the settler left behind continues without them, as worlds do. And the distance between the person on Mars and the life they knew on Earth widens not only in kilometers, but in time and shared experience and the accumulated small moments that constitute belonging somewhere. Looking up at the night sky from Mars, finding that small blue-white point of light that is Earth, knowing that every person you have ever loved, every place you have ever felt at home, every memory that constitutes the continuous narrative of your life is contained on that pale dot, and knowing that you cannot go back. That is not a poetic description of loneliness. It is the literal reality of what a Mars settler sees when they look up, and what they know when they look at it. The Antarctic Winter Over research stations represent the closest terrestrial analog to Mars in terms of isolation and confinement, and the psychological literature from them is sobering. Station crews who spend the Antarctic winter 6 months of continuous darkness, unable to leave due to weather conditions that make evacuation impossible, show consistent patterns of psychological decline. Researchers studying these populations identified what they called the third quarter phenomenon, a period roughly 3/4 of the way through the Winter Over mission, during which psychological functioning, group cohesion, and individual mood reach their lowest point simultaneously. Depression increases, interpersonal conflict intensifies, sleep deteriorates further, cognitive performance on certain tasks declines measurably. The Antarctic stations have rescue options. A sufficiently serious medical or psychological emergency can trigger an evacuation flight in the most extreme circumstances, at great risk and expense. But the option exists. The winter ends. Every person at an Antarctic station knows that when the season turns, the planes come back, the ice runway opens, and the world outside returns. The confinement is finite. The horizon, however distant, is visible. Mars has no horizon of that kind. There is no season that brings the supply flights back more frequently. There is no period at the end of a defined mission when the shuttle arrives and the crew goes home. For a permanent settler, the station is the world. The small group is the entire society, and the confinement is not a phase of a career, but the condition of a life. The compounding factor that the analog simulations cannot fully replicate is time. 8 months in HICs produced measurable deterioration. The Mars 500 simulation showed similar patterns across 520 days, but those studies have endpoints. The participants knew the endpoint before they began. The knowledge of an ending is itself psychologically protective. It allows the mind to frame the experience as finite, to pace itself, to maintain a future orientation that sustains motivation and prevents the particular despair that comes from believing the current situation is permanent. Permanent Mars settlers cannot frame their experience as finite. There is no scheduled ending. There is no date circled on a calendar that marks the transition back to a larger world. The psychological literature does not have good data on what this does to human beings over decades, because human beings have not done it before. The analog studies offer a glimpse of trajectory. That direction is clearly downward, but they cannot tell us where that trajectory ends when the mission has no end. All of this, the biological cost, the medical cost, the psychological cost we have just described, requires one thing to continue existing: money. And that number will make you ask, who is truly benefiting from this dream of Mars? When a new city grows in America, it generates its own economic justification as it grows. Tax revenue from property and commerce funds the roads that enable more commerce that generates more tax revenue. Natural resources in the surrounding region, timber, minerals, agricultural land, water, create industries that employ people who spend money, that funds services that attract more people. Tourism brings outside money in. Real estate appreciates as demand increases. The economic engine, once started, develops a self-sustaining momentum. The city does not need to import every calorie consumed by its residents from a location 10,000 miles away. It does not need to manufacture its own air. It grows because the environment surrounding it cooperates, at least minimally, with the project of human habitation. A Mars colony has none of that, not one piece of it. The cost of delivering 1 kilogram of cargo to the Martian surface under current technology runs between $10,000 and $100,000, depending on the mission architecture, the launch vehicle, and how the accounting is structured. SpaceX's Starship, if it achieves the cost targets Elon Musk has publicly stated, might bring that number down toward $1,000 per kilogram, a reduction so dramatic it would represent one of the most significant cost breakthroughs in the history of spaceflight. And even at $1,000 per kilogram, the economics of supplying a Mars colony remain extraordinary in the most literal sense of that word, outside the ordinary, beyond any economic framework that has ever governed a human settlement anywhere on Earth. A colony of 1,000 people requires food, at roughly 500 kilograms of food per person per year, as a conservative estimate for a population doing physically demanding work in a high-stress environment. That is 500,000 kilograms of food annually, assuming the colony cannot yet grow enough of its own. At $1,000 per kilogram, that is $500 million per year for food alone, for 1,000 people, before accounting for replacement equipment, medical supplies, spare parts for every system that breaks down, the enriched uranium fuel for the nuclear reactor, the medications that expire and must be restocked, the tools required for construction and maintenance, the electronic components that fail in a radiation environment and must be swapped out. The number does not converge towards sustainability as the colony grows, because growth requires more resources, which requires more supply flights, which requires more cost, which requires more funding from somewhere. The economic logic that makes Earth cities viable, the self-reinforcing cycle of local resource extraction, local commerce, local value creation does not apply to a planet where the environment produces nothing a human economy can use without first spending enormous energy to make it usable. What could Mars export to justify the expense? The question has been examined seriously, and the answers are not encouraging. Martian minerals exist, but the cost of extracting them and transporting them across interplanetary distances makes them economically non-competitive with the same minerals extracted on Earth. There is no mineral on Mars rare enough on Earth to justify a round-trip shipping cost measured in thousands of dollars per kilogram. Tourism is theoretically possible. People pay extraordinary sums for extraordinary experiences, but the market for $10 million tickets to spend months in an underground bunker, breathing recycled air and eating hydroponic lettuce under constant radiation exposure is, to put it gently, not large. Intellectual property and scientific knowledge generated on Mars could, in principle, have value. But any technology developed on Mars could be developed more cheaply, more safely, and more quickly on Earth by researchers who do not have to spend half their cognitive bandwidth worrying about whether the reactor is still running. The dependency chain is not a phase the colony passes through on its way to self-sufficiency. It is the permanent condition of a human presence on Mars for any timescale that honest engineering analysis can currently envision. Air processing requires components manufactured on Earth. Water extraction requires equipment manufactured on Earth. The nuclear reactor requires fuel processed on Earth. Medical supplies come from Earth. Electronic components come from Earth. The colony breathes, drinks, eats, and maintains itself on an unbroken supply line stretching across a minimum of 55 million kilometers. with resupply windows opening only when planetary orbital mechanics allow roughly every 26 months, when Earth and Mars reach favorable alignment for transit. What this means in practical terms, a Mars colony is not a colony in any historical sense of that word. Historical colonies, however exploitative or unjust their origins, at minimum extracted something of value from their location that could sustain the enterprise economically. The term implies a foothold that becomes self-supporting, that draws on local resources to eventually reduce its dependence on the mother civilization. A Mars settlement does not and cannot do this on any realistic near-term horizon. It is, accurately described, an extremely expensive and extremely dangerous space station that happens to be on a planetary surface rather than in orbit, dependent on Earth for everything that keeps its inhabitants alive, with no prospect of that dependency ending. At least at an underwater military base, you have water readily available, though, admittedly, the wrong kind. But here is what actually stops me. Not the cost, not the engineering. It is the argument used to justify all of this that Mars is humanity's backup plan. And when you look at the actual numbers, that argument is not just wrong, it is dangerous in a way that is subtle and surprising. The argument for Mars colonization that resonates most widely, that appears in the speeches of its most prominent advocates, and in the popular imagination of its supporters, is not primarily about scientific discovery or economic opportunity or the romance of exploration. It is about survival. The argument goes like this: Earth is fragile. Civilization is fragile. A single catastrophic event, a large asteroid, a runaway pandemic, a nuclear exchange, an accelerating climate collapse could end the human story entirely. Mars, as a second inhabited world, makes humanity a multiplanetary species, and a multiplanetary species cannot be wiped out by any single planetary catastrophe. Mars is the insurance policy. Mars is the backup. It is a compelling argument. It is also, when examined carefully against the actual physical conditions of both planets, almost precisely backwards. Consider the comparison. Honestly, Earth after a full-scale nuclear exchange, the worst-case scenario in the category of human-caused catastrophes, is a planet with a damaged but breathable atmosphere, with surviving liquid water in rivers, lakes, and oceans, with a magnetic field fully intact and continuing to deflect cosmic radiation, with one standard gravity maintaining human physiology, with soil that is contaminated in affected areas, but arable in vast regions that received no direct impact, with temperatures that are survivable with adequate shelter even under the worst nuclear winter projections, and with a surviving biosphere that, however damaged, contains the ecological machinery needed for recovery over decades to centuries. Mars on an ordinary Tuesday with no catastrophe, no exceptional event. Nothing unusual occurring, has an atmosphere that cannot be breathed and that exerts pressure lethal to unprotected human physiology. No liquid water anywhere on its surface, no magnetic field, radiation levels 100 times above safe human exposure thresholds, gravity that progressively destroys human bone and cardiovascular health, soil laced with perchlorate at concentrations thousands of times above safe limits, temperatures averaging -62 degrees Celsius with daily swings approaching 100 degrees, and periodic global dust storms that can eliminate solar power for months. Post-nuclear Earth, in other words, is dramatically more survivable than Mars on its best day. The backup planet, in any survival scenario involving a catastrophe that leaves Earth partially habitable, is strictly worse than the damaged primary. The only scenario in which Mars becomes preferable to Earth is one in which Earth becomes less survivable than Mars, and for that to happen, Earth would need to lose its atmosphere, its magnetic field, its liquid water, and its gravity simultaneously. No plausible catastrophe scenario produces that outcome. The opportunity cost argument compounds this. NASA estimates the cost of establishing a permanent Mars colony at between $500 billion and $1 trillion. The Intergovernmental Panel on Climate Change has estimated the total investment required to adequately address climate change and transition global energy systems to sustainable sources at roughly $3 to $5 trillion over 30 years. These numbers exist in the same order of magnitude. The money is not unlimited. The engineering talent is not unlimited. The political attention and institutional capacity required to execute on planetary-scale projects is not unlimited. Dollars and engineers and political will directed toward Mars are dollars and engineers and political will not directed toward the problems that are actually making Earth less habitable right now, this decade, on a timeline where the interventions still matter. If the goal is to ensure long-term human survival, the most direct path to that goal is making the planet we already inhabit, the one with breathable air, liquid water, a protective magnetic field, one standard gravity, and 4.5 billion years of accumulated biological infrastructure more resilient, more sustainable, and better protected against the categories of risk that actually threaten it. The backup planet argument, taken seriously as a survival strategy, directs resources away from that goal and toward a planet that cannot serve as a backup under any realistic catastrophe scenario. The philosophical question that remains when the economics and the physics are both accounted for is the simplest one. We have a planet, the only one in the known universe confirmed to support complex life, the only one that evolved the conditions our biology requires without any engineering at all, the only one where a human being can walk outside and breathe and feel the sun on their skin without a pressure suit and a radiation shield and a nuclear reactor keeping them alive. We have struggled, across all of recorded history, to manage that planet wisely. We have damaged its atmosphere, depleted its resources in some regions, destabilized its climate systems in ways that are already causing measurable harm, and that will cause more harm over the coming century unless addressed. If we cannot take care of the most habitable planet in the solar system, the one that asks almost nothing of us in exchange for the extraordinary gift of breathable air and liquid water and survivable temperatures, what exactly is the basis for confidence that we will do better on a planet that asks everything of us and offers almost nothing in return? Perhaps the answer is not out there, on that rust-colored point of light in the night sky. Perhaps the backup planet, the one that is green and warm, that has water and air and life embedded in every layer of its surface, is already turning around the sun right now, and we are already living on it. But here is the strangest thing about all of this. Despite everything pointing toward Mars being nearly impossible to inhabit, humanity simply cannot stop dreaming about it, and perhaps that is actually the most interesting part. So, do we have an answer? No, and that is exactly the point. Science shows us the challenges. It does not show us the ceiling. Every number in this video, the radiation levels, the pressure differentials, the bone density loss, the perchlorate concentrations, represents the boundary of what we currently know how to solve, not proof that it cannot be solved. There was a time when powered flight was a physical impossibility, when transplanting a human heart was science fiction, when the idea of a global network connecting every human mind to every other was simply not a category of thought available to the people living before it existed. The people who said those things were impossible were not wrong to say so. They were working with the knowledge they had. They just didn't know what was coming. We don't know what's coming either. A single discovery about radiation shielding, about low-gravity biology, about closed-loop life support could rewrite everything this video has argued, or it won't. And no one alive today can tell you which. The darkness between Earth and Mars is not a place of despair. It is where humanity's hardest questions wait patient, silent, cold. Tonight, when you look up and find that small red point of light that isn't just a planet, That is the largest question our species has never learned how to answer.